Is the audio working? Can somebody confirm? No, 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 no. Okay, let's start. This is the first fully online lecture of the physics course. So we'll see how this goes. Give us any feedback you can. Let us know if the audio is not working, if you can't see me, if you can't see the slides, any of these problems. I do know that I'm going to start the recording as well. Here we go, start recording. So if anything goes wrong, from now on the recording will also be on the website afterwards. So not all will be lost, but hopefully we'll be able to do something semi-live here. Okay, so we're in the part of the course where we're going to talk about parallel programming. So we're trying to improve the performance of our codes using multiple cores. And as Marcelo was talking about previous lectures, most computer architectures these days have at least a couple of cores, and supercomputers have many cores, but they're divided into separate nodes. And those different nodes will have multiple cores each, but will have to communicate with one another quite explicitly if you want to use more than the number of cores on a single node. What we're going to talk about today, though, is just what happens on a single node with multiple cores, which is very similar to what would happen on your typical laptop or workstation. So the idea of this is it's called shared memory programming, and that's because of the following picture of the system. So the idea is you have a computer, you have a laptop or a node in the supercomputer or a workstation, and it has several cores. So in this picture there are 8 cores, numbered 0 to 7, and they all see the same memory. So your laptop has a certain amount of memory, 4 gig, 8 gig, whatever, and a certain number of cores, often at least 4 these days, and they all can operate at the same time. All those cores can do something different at the same time, but they share this memory blob, this location of memory. And so if core 0 writes something in memory, core 1 can see it. That's going to be very different when we look at message passing interface. When we look at multiple nodes running at the same time, they do not share the memory, but that's not what we're looking at this lecture. Excuse me. So this lecture we're going to look at this scenario. One machine, multiple cores, all seeing the same memory. What that means is, although each core can do something different, they can communicate with the other cores by putting something in memory, and the other core can read that. So memory is going to be the way that these cores communicate to some extent. Just a little bit of terminology. Each of the cores can do something different. What they are doing is called a thread of execution. So it's like each core is running its own program, but they're running all at the same time. And at the same time, they can access this shared memory pool. Okay, so this only works for shared memory systems, so only works for that single node concept. And what's nice, the way we're going to program these cores in C++, and you can do the same in Fortran and C, is use a technology called OpenMP. OpenMP stands for Open Multiprocessing. It shouldn't be confused with OpenMPI, which is an MPI implementation that we'll talk about later. This is OpenMP, period, and it's for shared memory systems. And the way it works, and what's nice about OpenMP, is that you can take a non-parallelized code, so what we call a serial code that can only run on a single core, and you can find as a programmer the parts of that code that could be run in parallel. That's something you would have to do as a programmer, figure out what could be done in parallel by multiple cores without stepping on each other's toes. And then you add pragmas or compiler directives to the code to tell the compiler that that particular section can be done in parallel. And then the compiler will do everything else. It will create the threads. It will divide up work among the threads if you tell it to. It will make sure that the threads keep busy. But we have to tell, as a programmer, what can be done in parallel and what cannot. The website of OpenMP, it's been around for a while. And this screenshot is a little old, but it has lots of goodies in it. It has examples. It has the specification of OpenMP. One thing I should warn you against, as with any specification or any standard, when a standard comes out, so I think OpenMP is at 5 now, version 5, not all compilers will have everything implemented of that. So what we're going to look at is actually fairly basic OpenMP. And we're not using any of the newer versions, so you can be sure that that will work on pretty much any modern compiler. But if you ever want to do things like use OpenMP for advanced features, offloading to a GPU, for instance, is something that is possible in OpenMP now. We're not going to cover that because that's later versions and assumes a certain architecture of your machine. So OpenMP, how do we do this? How do we work with OpenMP? And so it's not, there are several aspects when you move from just a serial code to a parallel code, and we'll see lots of things that are different. What is of course not different is that you write code, you compile code, and you run code. That we've seen that throughout, even for serial code. And so each of these 3 steps, the writing of the code, the compilation, and the running of the code, have to be slightly altered when you're doing things in parallel. In code, you will have to tell the compiler, for when we're using OpenMP, what part are parallel or can be done in parallel. The compiler will make them parallel, but you will have to say this particular set of instructions can be done by multiple cores at the same time. So we do that in the code, and then the compiler will parallelize the block. So when we're compiling, we'll have to tell the compiler that we want it to do that. So in the code, we'll have things that looks like pound pragma OMP, which are compiler directives. But the pragma kind of indicates that this is sort of optional. It's a pragmatic thing. If the compiler isn't told to pay attention to these pragmas, it will skip them. And so we have to tell the compiler, hey, pay attention to these pragmas and do what they say. And for G++, that means adding a flag to the compilation that is -f OpenMP. And in fact, even the link command, so if you're linking it, you still have to say -f OpenMP. And that's because OpenMP is both a language extension, those are the pound pragma OMPs, and a library that makes sure that all these threads are created and that tasks are given to the different cores. That's a library. So we have to both include it in the compilation and in the linking. Even when that's done, so now we have an application, we have an executable. When we run it, we might want to control how many cores it's actually using. Now, if this was the only thing that is running on your machine and you have 8 cores, you would want it to use all 8 cores. That would make sense. But maybe you have multiple things going on and you want to reduce the number of threads that are being used, so the number of cores that are used. So you can do that while running by setting an environment variable. And so the environment variable is called OMP num threads with underscores in between there. And you set it to the number that you have to do. So we have a number of example codes. They're on the teach cluster. So if you want to follow along, you can SSH to the teach cluster. I would suggest you work on Scratch for reasons that will be obvious later. You can clone the code of this lecture as well as of the next lecture at Scinet courses PHY1610 OMP. That clone will create the OMP directory, so you cd in it. We'll need certain libraries or certain modules to be loaded. So if in the OMP directory there's going to be a setup file, you can do source setup, and that will basically load the modules that you need. The code obviously will have a makefile because we've been using makefiles throughout, and so you can do, and say you only want to compile one of the specific examples, you can do make OMP HelloWorld, and it will compile HelloWorld for you. And you will see when you do that, all these things come by. So if you looked at the code OMP HelloWorld.cc, you would see pragma OMPs in there. You'd see that the compilation commands have -f OpenMP in them, as well as the linking commands. And if you run it, you would have to use OMP num threads. So here's that first example. So this is a HelloWorld example. Anything you do, any new language or language feature you use, you should do a HelloWorld, apparently. And so it has a main function. It prints out at start of program, and then it starts printing out HelloWorld from threads. The idea is that there's a thread number then, and so we've got a pragma OMP parallel. Apparently something's going to go in parallel, and some thread number. This is kind of the simplest OpenMP example you can think of. Went too fast. So if you wanted to compile this, I can say G++, standard C++14, as we've been using throughout the course. Optimize, so -O to, and then I want the output to go to OMP HelloWorld. That's the executable. The source code is OMP HelloWorld.cc, and I have to give this flag -f OpenMP. If I don't, it will create a serial code. It will basically ignore all the pragma OMPs. Then to run it, if I run it with alternatively, if you've cloned this repository, make OMP HelloWorld will do the same thing. Then we're going to export OMP _num _threads to 1. That means that we'll want to use only one thread. So we'll want to see what happens if we don't do parallelism, but just run the code in serial first, and then we can run it with /OMP HelloWorld. Okay, so if we do that, the first thing, that's the first line here, one thread, and we run the program, it says at start of program, HelloWorld from thread 0. If we increase the number of threads to 8 and we run the program, it will say at start of program, and each of the threads will print out a message. So let's look at this code again and see how it really did this. So what happens when you start a threaded code, and so the threaded code is anything that uses multiple threads, is that it starts with a single thread of execution. So one core is busy, it's given one thread, and that's how it starts. So when it enters the int main, there is no parallelism going on here. It's just a serial code, and the serial code prints at start of program, and that's what we see here. But something funny happens when it hits the pragma OMP parallel. What happens is that at that point, the OpenMP runtime will start a number of threads. So in this case, because OMP numthread was set to 8, it will start 8 threads. And those 8 threads are by the operating system actually distributed over the cores that you have. So if you have 8 cores, each of these threads is going to run on each of the cores. The operating system makes sure that if one core is busy, it goes to another core, etc. Basically, you don't have to worry about assigning threads to cores. You just have to worry about creating threads. But it doesn't mean that if you created 8 threads, but you had 4 cores, what would happen is that each core would get 2 threads. So that all of that sort of happens automatically. So that's not it's not something you ever have to worry about when you're programming. You just have to make sure that there's a number of threads spawned that is appropriate for the machine you're running on. So I'm assuming here there's 8 cores. I'm running with 8 threads. So it's launching those threads, and each of the threads gets to execute the same block. So this pragma OMP basically hooks into the next code block. So this is between 2 curly braces here. The point of this code is to write out what thread number they are. So they're each going to execute exactly the same code. Each thread is going to get the same code, and so each of them would do the same thing and would print hello world from thread. The thing that distinguishes them is that each thread can ask what its thread number is. So not only are there threads, the threads know their number. And so they're numbered from 0 to, in this case, 7. And so each of the thread knows whether there's 0, 1, 2, 3, and I get that number by calling a function. The function is OMP get thread num, and this function is defined in a header file. That should not surprise you, and the header file is omp.h. So that's why we have this omp.h included, so we can call this library function. And so each of them does it at the same time, each print hello world. One thing that is a little bit funny, perhaps, if you look at this first, is that they seem to be going in random order. So I have thread 0 first, that might be expected, then thread 6 writes something, then thread 3. And that might be surprising and a little bit counterintuitive, but this is parallel programming. All of these threads are running at the same time, and they're all trying to write to the screen at the same time. But nothing actually happens exactly at the same time. Some threads are going to be like a fraction of a millisecond faster than the other thread, just by sheer luck, if you want. So because it's sheer luck, and it really depends on what they were doing before, but for all the intended purposes, it's luck. It just so happens that thread 6 got its message to screen just a little bit before thread 3, etc. So that if they're running at the same time, and you're writing to a shared resource like the screen, you can't count on the order in which things are done. And that's something that is typical for parallel programming. If you want to have your cores run at the same time, there shouldn't be any dependencies, because otherwise one core would have to wait for the other. But as a result, because they're doing things at the same time, the output in a case like this could be in a random order. It's not a wrong order, it's just random. Okay, so OpenMP, it's both a language extension, so those are the pragma OMPs, they can launch threads. Also a library, so the omp.h header gives access to library functions. There's a whole bunch of them, but here's some of the most common ones. You can ask how many threads have been spawned. So in the case of before we had 8 threads, this should give 8. We can ask the number of each of the threads. It starts indexed at 0, but we're kind of used to this because we're working in C++. Excuse me. And those are two very common ones. We can also set the number of threads. Now, usually you want to set the number of threads with the environment variable, because that way it's not hard-coded into your code, and you could try the same parallel code with different numbers of threads and see what works best. But it is possible also within the code to set the number of threads to be used for the next parallel session. So there's OpenMP get num threads. And so that's number of threads. Now, as I said, the number of threads and cores in a machine do not have to be the same. The operating system sort of makes sure that they are evenly divided. But if you do want to know how many processors are in your machine, you can ask that to the OpenMP library as well, and that's OpenMP get num procs. Okay, so here's another example that uses a little bit more of these library functions. So again, we are going to do a kind of HelloWorld. We're going to run from each of the threads. That part is the same, so they're each going to print out their thread number. Now, the parallel OpenMP latches on to the next code block, but if there's no curly braces, that next code block is just the next line of code. So in this case, the Pragma OpenMP parallel only works for this first line of code until the semicolon, because I didn't do curly braces. It's very, very much a C++ kind of thing in this case. Then after they've all printed out their threads, I would like to know how many threads there were. So I haven't hard-coded it here. It's set by an environment variable. I would like to report how many there were. So the last thing is done. There were a certain number of threads in this code. And I only want this to be printed out once. So I don't have it part of the parallel code. Excuse me. Okay, so what happens here is that we're going to make this code. The code is called OpenMP num threads 2. Set the number of threads to 3 for the only purpose that it will still fit on the slide here. More than 3 would fall off the slides. And we're running it. So what we see is at the start of the program, that's our first line, we see the message from each of the threads, and then we get that there was 1 thread. Now that's strange, because there were obviously 3 threads. So what happens? And what happens is that this function gives you the number of threads that are active. When we're not in this parallel region, the threads have been disappeared. So they appeared when I said parallel. There's 3 threads, each of them doing something. And then they're closed after the parallel thread is done, the parallel region is done, and then we're back to serial. And in serial there is 1 thread. So it's true. But that's kind of annoying. That's not what we intended. We want to know how many there were in the thread. Okay, so how do we get this out? How do we get the information out of the parallel region? Because in the parallel region we can ask OpenMP get num threads and it will give us the right answer. But then as soon as the region stops, where does this answer go? And so what we will try is to just store that answer in a variable. So here's a attempt. I'm creating 2 variables, and here's a variable t and n threads. And inside the parallel region, I'm going to store the number of threads into the variable t. And if t is 0, I will ask for the number of threads. So the idea here is that I could have every thread print out how many threads there are, but now I get 8 messages for the same information. So I just want one of the threads to do this. So one of the threads is doing this and storing its result into a variable called n threads. And then after the parallel region, I can ask how many n threads there are. Now you can see there's some other stuff that has appeared here, and we'll talk about that in a second. But that's the idea. I'm going to store my variables, the results of these library calls into variables, and then after the parallel region, since the variables still exist, I can ask what's in them. And so now what are these extra clauses? There are a couple of different types of variables or variable access that you can declare, and it's kind of weird. We're going to do shared memory parallel programming, which means all the threads can in principle see all of the memory, but that's not always great. sometimes you want a thread to use a variable just for itself and then not to be visible to others. And so there is a programmatic distinction between variables that do live in the shared memory, and that is to say that you can see them from all the threads, and variables that are private to each of the threads, and that other threads can't see the value of that variable for other threads. And so shared and private is how you indicate this. So if you have a shared now the compiler at first doesn't know which ones should be which, and so you will have to say which variables can be seen by all threads that respond and which variables should be just seen by the thread itself. And so if they're supposed to be visible to all threads, we will call them shared. This does one more thing. If it's a shared variable, not only can these threads inside the parallel region see it, also the thread outside, so the serial thread, can also see it. It's essentially just the same variable. It's kind of what you would imagine from shared memory programming. And threads is a variable. All of these threads that have been launched here can see that variable because it's shared variable. So shared and threads sort of expresses that. The other variable I have here, t, should not be shared among all of them. They should not be shared because if t is assigned to OMP num threads, each thread has its own number. And so if all of the threads are starting to try and write to the same variable at the same time, that would cause clashes. And pretty much anything could happen. We call that a race condition. What we want here is for each thread themselves to determine their thread number and store it in its own variable. So what happens with these private variables in more detail is that t here is a variable. It lives in sort of a shared space in principle, but it's only visible to the serial thread because that's all that exists outside of the parallel region. When you hit the parallel region, OpenMP creates, in this case, 8 versions of that same variable t. Each of them can be used separately by each of the threads. So as far as the threads are concerned, they see one of those variables, but because there are 8 threads, there are actually 8 of these variables, and each of the thread has its private version of it. So because they're private and have their own version, when they assign to it, they assign to their own version. They don't step on the other's foot. And so we can now ask whether this thread is 0, and that will only be true for thread 0, and it will store n threads. N threads is shared, but only one of the threads is actually writing to it, so no race condition there, and we get n threads out. This is the same thing I was just saying in words. So shared variables are what you would imagine shared memory programming is about. Every thread can see them. You can write it to them at the same time, which can cause trouble. Race conditions. If you're reading things, it doesn't really matter. Although sometimes for performance you might have your own copy, but that's an optimization issue. Private variables are important if you want each thread to get their own separate version of a variable. So we saw t has to do that. What is very funny about private variables is that they're not copies of the original variable. They're 8 versions of it, and so and each of these versions is actually not initialized at all. So even if I set t to 0 before entering the parallel region, with private t, each of the threads would not have their t value would not have the value 0. Similarly, any value you assign to a private variable outside of the parallel region, so when you exit that parallel block, it's gone. It doesn't exist anymore. It's not even so that thread 0 is the same as the serial thread. Those are different. Those don't see the same variables either. Now, you don't have to say what variables are shared or private. You can have the compiler choose for you. And sometimes those are sensible choices, and sometimes they're not. And so especially when I find when you're starting with this, it really helps to think about what variables should be shared and which ones should be private. And so to force yourself to do that, you can have this option default none, which doesn't use any of the defaults that the compiler uses. So that's why this code looks like this. So we have pragma OMP parallel, default none, So the compiler won't choose, and now I have to say for all the variables that occur in this block, whether they're shared or private. If I don't, the compiler will say, hey, you're using variable t, you didn't say what it was, I don't know what to do, and it will stop the compilation. It'll give you an error until you specify for each of the variables which one they are. So, oops. Yeah. Okay. All right. So we have the code. We have set the variables. We can run it, and when we run it, and here's a slightly simpler version of the code that doesn't print per thread. It indeed says there are 3 threads. So this works. There's no race condition. There's a private variable that stores the thread number. Thread number 0 stores end threads, and threads exist after. So the shared variable still exists and gives the right answer. Okay. Now, in C and C++, we can do something nifty that you can't do in Fortran. You can declare your private variable t here inside the block, like so, int t. Now, what that does, it doesn't exist outside anymore, so I can't even specify that it should be private. But the big gain here is that any variable that I do declare inside of the parallel region is automatically private. And you can think of this as a declaration of a t, and each thread is declaring its own t. And so in that sense, it's private. And that's sort of a model, a way of thinking about it. So that means that I only have to worry about the shared stuff. And in many cases, in nicely written C++ OpenMP, you almost never have to say that something is private. Yeah. Okay, now one thing that is a little bit funny and that can be improved upon is that we only have one thread setting the end threads variable, but really we do not care that it is thread number 0. We chose thread number 0 because no matter how many threads I have, I always have at least one thread, so I always have at least one thread that is called thread 0. So thread 0 always exists. But I don't really care. In fact, I'd rather just have the first thread that gets to it to execute it. And to do that, you can use another pragma. So it's called pragma OMP single. The pragma OMP single again latches on to the next code block, or if there's no code block, just the next line of code. And what it does, it makes sure that that line is only executed by one thread only. Other threads, and basically it will be the first thread that gets there, gets to execute that. The other threads, when they get there, will skip it. So that's what's happening here. I've got my parallel region again. All I have to have is a shared number of threads, and then only one thread stores the value of OMP get threads in end threads. And that works just the same. Okay. But it's a much simpler code in a sense. So this can be useful to have things like maybe you want to print, maybe you have a parallel code, there's an iteration going on, you want to know the iteration number. You don't want every thread to print out the iteration number, just whatever thread happens to have some time. This is the way you would do that. Okay, so that is a lot of the basics of parallel programming, but we just took a piece of code and then had every thread execute the same code. That is a little bit weird because it was already executing the code in serial. So why would we want to do 8 times the same thing? So what this parallel programming is going to be good for is if we have more than one thing to do, like several cases with like maybe an array of cases, an array of data, and for each of the array elements we want to do something, we could split up that array and have different portions go to different threads. So loops. Loops are very common in scientific code and are the prime target of parallelization in many cases. And so let's look at a code here. We do the same thing as before. We have, but instead of having one case, we imagine we have 16 cases. And the only difference between the cases is that the I number goes from 0 to 15. And the thing to do for each case is to print I. But you have to think about this as a prototype of I are actually pieces of data, and what I'm doing is a little bit more interesting than just printing. But this way it's easier to see. So what this does is we have OMP parallel, default none, private, shared. By the way, if you want to print out into the inside of the parallel region, standard out, so cout is a variable, and it will have to be declared shared for us to be able to use it. Just in case you're wondering. And because it's defined outside, that's what we have to do. Okay, so what does this do? It determines the thread number, and then it counts from 0 to 15 and prints out that each thread gets a certain I. So if you do this with two threads, OpenMP loop 1 is the code, we run with two threads, we get 32 cases. So because every thread gets this for loop from 0 to 15. Let's look at the code again. Let's see. Here, yeah. Let's look at the code again. See, this code block is done identically by every thread. So every thread counts from 0 to 15. But that's not typically what we want. We want to divide these 16 cases up into the different cores. Okay. So, and in that way, we would have less work to do per core, and so each core will be finished faster, and therefore the throughput will be greater, the speed will be greater, and we actually get some use out of these cores. So we want to divide this range between 0 and up to 15, and divide it up and give different cases to different threads. And OpenMP is very, very suited to that. The way you do that is you use another construct, another pragma called OMP4. So it looks like this. So we're already in our parallel region here. But then before the loop, we were going to say, not all threads should do this loop in the same way. Each thread should take a portion of this loop and only do their portion. And that is done just by putting pragma OMP4 in front of this loop. And so pragma OMP4 will say, okay, I'm in the parallel region. I have, say, 8 cores. I see you want 16 things done. So I'm going to give two values of I to each core. And let's see how that works out. So I'm making the OMP loop 2 executable. That is that code. I set the number of threads to 2. And now when I run it, I get 16 cases. Some of the cases were assigned to thread 0. Some of the cases were assigned to thread 1. We again see this the randomization of the output. But if you look very carefully, you will actually see that the first 8 cases were given to thread 0 and the last 8 cases were given to thread 1. So what it does is this OMP4, pragma OMP4 divides up the iteration space in large chunks and gives one big chunk to each of the threads. Okay. Now this is still kind of trivial, so I want to look at something less trivial. Imagine that we want to do a blast call, and so we're going a little bit against the grain here because we've told you not to write your own linear algebra routines and to use libraries like BLAST or OpenBLAST or MPKL, and so we're straying from that just because these linear algebra routines have nice little loops that are very useful to illustrate what you can do with OpenMP. And so I've written my DAXP here. It takes so there's A times X plus Y, right? So here's our A. X is going to be an R array in this case. Y also an array, so 2 vectors, and then there's an output vector Z. We'll see the code for my DAXP in the next slide, but this is the driver routine. So we'll take 10 million elements in our arrays. Here are our 3 arrays. We set A to some value that we sort of random. There's a tick-tock routine that's part of the code that measures the time. And so we initialize our vectors in init, and then we run the AX plus B, and then we see how long it took. So here's the initialization. It's kind of not random, it's kind of arbitrary what I chose here. X is Y squared, and Y is Y squared minus 1. That's just X is I, sorry, the index is the same as X. So I squared is Xi, and Yi is I plus 1 squared. That initializes it just to have something in it, so it's not entirely trivial. We're not just adding zeros and then we can't see if it's right. Here's my DAXP. It takes the 3 arrays and the value of A, and it just has a loop over the number of elements. And I'm not assuming that all the arrays are equally long, so I'm only going to do the minimum of the sizes, but it's probably better if we insisted that they were all the same size. In any case, n is the smallest size of each of the three arrays, and so we're going to fill zi with a times x plus y for that particular index. It's a nice for loop, and one of the things you can see in this for loop, and that's what the task of parallelization in OpenMP always boils down to, is we can see that this can be done in parallel. Every I value can be done separately, doesn't influence the other I value, and so there's no reason why this couldn't be done by multiple cores at the same time. So as I said, that's the point. The point is to try and find what's called the concurrency. What can be done at the same time? What doesn't depend on one another? And if we find that, that's where we're going to put our pragmas. Okay. Then the other thing that we have to do, but that's what OpenMP is good at, is to divide the work over the threads. And then we have to decide, okay, that parallel region, what variables need to be shared and what needs to be private. In other words, what does each thread need to know from the sort of global shared space, and what do they need to know about just for themselves. So the initialization also had a for loop. It also is independent. Each for loop iteration was independent, and so that can also be parallelized. So we can parallelize this quite straightforwardly by saying, okay, there's going to be a for loop. We need threads for them. So we first have to create the threads by pragma OMP parallel. We don't want to assume anything in terms of shared and private, so default none. And then we need to be able to access certain variables inside the loop. And what we're using is x, y, n, and I. But I is already declared inside of the loop, so that's going to be private by default. We don't have to worry about I. So we have x and y, so they are shared. But then if you look carefully, we're also using n. So n also better just be shared. N is not going to get changed. But we've just declared it as a variable, we still have to say that it's shared if you want to be able to use it. So we've got n there. So when we enter the curly brace part, that's when we have our threads. But if we didn't put it OpenMP4 here, every thread would start initializing the array from 0 to n. And so it wouldn't be any faster because each thread is going to do it the same way. So we want to divide up this work, and we put a pragma OpenMP4, and what OpenMP will do behind the scenes for us is say, okay, I can see what your value of n is here. You're telling me by putting it in this for pragma that all iterations are independent. I'm going to assume that, and I'm just going to give the first, say if you had two threads, the first half to one thread and the other half to the next thread. Okay? So that's it. That will do. The MyDexP, similarly, every part can be done independently. And so we have a parallel region here and a work sharing pragma after it, and every I is done separately and more or less at the same time. And at the same time means up to sort of timing issues, right? Now, there's a few things that are handy because this happens very often. You have a for loop, you want to add it, you want to add threads to it. So here's a few things that can be done without having to be basically reducing the amount of boilerplate to write these things. First, if you had a constant somewhere, you don't have to say if it's shared or not. A constant is the value it is. So the compiler can substitute a value for it. And that is actually sort of hardwired into OpenMP. If instead of a variable you have a constant, it is automatically shared and you don't have to say that it's shared. So we saw one case of that here. We saw that n really could be a constant. If it were a constant, I would not have to say if it's shared or not. And how do I make it a constant? I just put a const keyword in front of it, right? We'll see how it works out in the code in a second. Another thing that is very common is that you start a parallel region with a number of threads, and then the very next thing you do is divide work over a for loop. And so there's a shorthand for pragma OMP parallel, then followed by pragma OMP, and it's just pragma OMP parallel 4. You just combine the two. Not every pragma can be combined like this, but this is so common that it is very that it's allowed. So what that means is that to have done that in the bottom case here, oh no, this was what I had. How do I get it simpler? Okay, here we go. So the first thing is I put constants in front of the int. Then I don't have to say n in the shared cases anymore. That's nice. Because it's a constant, there is no, it doesn't matter if it's shared or not. It's always the same value anyway. And so the compiler can figure out what it should do for it. And then, as I said, we can combine parallel and for. So it looks like this. Pragma, OMP, parallel, for, default, none, shared. And the same here. I just have to share a little bit more. And then, of course, I take out the empty lines. Now, I'm doing this sort of step by step because this is what's going on. You create a parallel region, you create threads, you divide the work. But on the other hand, once you're a little bit used to that, you just want to put pragma OMP parallel for in front of the for loops that are of which the iterations are independent. So that's great. But what is great about that is that this code, if you look at this code, if you leave out the pragmas, it's the old serial code. So the code is a lot easier so ideally, and not always, but ideally, if you write an OpenMP code, you start with a serial code and you put in pragmas. But if you left out the pragmas, it would still work as if it was the old serial code. And when you can do that, that is fantastic, because then you have a test case. You can do an integrated test or a unit test, and you say, let me run this with one thread, or not compile it with fopenmp at all, and it will still compile and give the old correct answer. Well, I don't know if that's correct, the old answer. And then I can switch on OpenMP. I can compile it with OpenMP. I can set OMP num threads. I can run it again and test if it's the same. And so the same code can be run in parallel or in serial by switching on and off pragma. We will see that this is essentially impossible for MPI code, but for OpenMP code, that is exactly what you get. And there's sort of a desire or a principle that you want this to be the case. If you can, you want your code to be working as your serial code with extra pragmas. You still have to know exactly what these pragmas do. If you don't know that these iterations are independent, if say xi depended on xi minus 1, I could write parallel and the compiler will take your word for it that they're independent, but they're not. And so I'm going to get the wrong answer when I do that. So you have to know also what shared does and what has to be shared and what should not be shared. All these aspects in writing the longer form of the for loop, you have to know about. Because you're giving the compiler the permission to assume a whole bunch of things. You need to make sure that that is correct. This, by the way, is also the reason why compilers do not auto-parallelize very well. Some compilers have flags that you can give and say, here's the serial code, just go make it parallel. And the trouble with that is that, yes, you're giving the compiler the permission to make it parallel, but at the same time, the compiler still has to sort of guarantee that it is given the correct answer. And so it starts checking assumptions of independence. And if there's, for some reason, if there's no clear reason why they are independent, it defaults back to a serial code. And so it can't know very well whether these are independent variables. So maybe in this case it would figure it out. But in general, it's much harder to see whether there's any dependencies. We don't know if I is secretly changed somewhere, or so the compiler is going to go, I don't know, maybe there's a dependency, I'm not parallelizing this. We are putting that in. That's why we have to do the work. We have to say, no, this is going to be independent. For some reason, we can see this because we wrote the code, right? And the compiler just gets the code. And so that's why we have to do it by ourselves. But the amount of work we have to do with OpenMP is to check those dependencies. And if we've checked that they're not there, it's fairly straightforward to implement. So here's an example of running this. So here's our MyDexy example. This is the serial version. I think I run this on the Teach cluster. It's pretty fast, 0.39 seconds. Then you do the parallel region, the parallel version, so that just has the pragmas. I export the number of threads to 16. I run it again, and it is 5.5 times faster. By the way, if we're going to do this timing, And we're almost out of time, so that's good. If you're going to do this kind of timing, you might want to make sure that nobody else is running on the same machine. So if you're doing this on the Teach cluster and you log in, so far you logged into the login node, and all the students are there at the same time. And so when you're running this with 16 threads and somebody else is also running it with 16 threads, this is going to go at least twice as slow. Because there's only 16 cores on that login node. So what it also means that as you're trying it again and again, you're going to get different timings, because it just happens that somebody else was or was not running. So to have predictable timings and to have a good way to profiling, you basically want to have some cores that are dedicated to just you. You're just running on those cores. On the login nodes, you can't do that, but on the compute nodes of the Teach cluster, you can. And so you could write a job and a job script and try things that way. But there is a faster way if you're just trying things out. We have a command called debug job, which gives you a temporary interactive session on one of the compute nodes. So you're on the login node, you type debug job, it grabs some resources from the compute nodes, logs you in there, SSHs you in there, and you get a terminal and you can work there. It's like you're logging in there, so you have to reload all your modules and all of that. But that's how it works. So the way it works specifically for the Teach cluster, and I just want to mention this, is that you have to say how many cores you want. So yes, each compute node has 16 cores, but if you just said debug job, it gets you onto one of the compute nodes, but only gives you one of the cores. And then the next student that asks the debug job gets the next core, which can still be good for independent testing because you're not sharing the core, but it's not very good if you want to scale up because you have only one core. So you have to say how many cores you want with -n. And as I said, if you give 8 cores and you run a program that is threaded, and you use 8 threads, they're going to be assigned to those 8 cores. They're going to be spread out over the cores. The operating system does that for you. If you didn't specify how many cores you got 1, you can still spawn 8 threads. The program will run, but it will run all threads at the same core. Already it will have that core interleave operations for one thread and go to another thread and another thread. And so that's typically even slower than just 8 times as long because the switching takes some time. So it's often not a good idea to overload the number of threads, so have the threads not be more than the number of cores. So if you want to run up to 8 threads, you should ask for 8 cores. You did it with the -n option here. You could go up to 16, in which case you get a whole node. Larger than that, you would get multiple nodes, and you can't use OpenMP. So if you tried a debug job -n32, you would get 2 nodes, but they don't share the memory. So you would have 16 nodes that can see shared memory and 16 other cores that can see another shared memory. But whatever you launch will only run on the first node. You will not be using the other one with OpenMP. If you wanted to do across nodes, we will have to do MPI, and we'll do that next week. Okay. If you're running on Niagara, so on our big supercomputer, you cannot get partial nodes. You always get a whole node. So you always get 40 cores. But you probably just want to try this out on a Teach cluster anyway. Okay, so these were the basics of OpenMP. We saw quite a bit. We saw launching threads. We saw variables that can be shared or private. We saw how to do work sharing for a for loop, which sped up the code. We did see a few odd things. We saw, for instance, that the speed up was not a factor of 16. And so that's a question. Why did that happen? So we'll have to answer that. There's also more complicated cases. All of these were cases where the iterations in the loop were completely independent, and that's fantastic. But it's a little bit like the embarrassingly parallel cases that Marcella was talking about last week. Those are not the only possible cases. So if there are certain dependencies, some of them can still be parallelized. But that, again, is a new chapter. So performance, why exactly did we not get a 16 times speed up? And more complicated cases of where iterations might have some dependencies. And what we also didn't look at is if the iterations have different things to do, we'll have to look at load balancing. So in the next lecture on Thursday, we will look at all those cases and figure out how we not just parallelize our code, but also parallelize it efficiently and correctly. Okay, so that's going to be the lecture of today. Let us know how the streaming went. If there was any issues, we can improve. This is all new territory for us. As I said, the recording will be online as well. You'll have that. Yeah, just give us your feedback as to how this went. Hopefully, we'll be able to do this somewhat effectively for the next little while until the end of term.